Let x and y have the joint density function f of x equal to x plus y, x between 0 and 1, y between 0 and 1. What is the conditional mean of y given x equal to 1/3? Sample exam number 7, question number 27 is we're asked to find the conditional mean of y given x equal to 1/3. First of all, we find the marginal f of x, and that's we integrate out y over the range of y of the joint density, and then that integrates to x plus a half. Then the conditional density is the joint density divided by the marginal density, which is this. So then to take the expected value, we take y times this joint density, which is what this is. Then this is a constant, so it can be taken out. And then the y is multiplied in. And then when you take the antiderivative, you get this. We need to evaluate it from 0 to 1, and you get 3/5. Number 28, let x1 and x2 be independent continuous random variables, each with density function f of x equal to lambda e to the minus lambda x, x greater than 0, lambda greater than 0. Let y1 equal to x1 plus 2x2 and y2 equal to 2x1 plus x2. What is the joint density function of g of y1 comma y2, where both y1 and y2 are positive? Number 28, we're asked to find the joint density of y1 and y2. And we're given that x1 and x2 are independent. So the joint density for x1 and x2 is the product of those two densities, which then gives us this. Now to complete the transformation, this is what we're given. So then you can sort of back solve this for x1 and x2, and you get these equations. Then the Jacobian of this transformation, the absolute value of the Jacobian of this transformation is this. You take the partial of x1 with respect to y1, partial of x1 with respect to y2, and etc. And then you take the derivative, and you get this, and the absolute value makes that positive. So then the joint density is you take these values of x1, plug them into the original density, which is what this is, and then you take it times the Jacobian for that transformation, which is 1/3. And then this all simplifies to this, which is the answer. Number 29, let E and F be events such that the probability of E is 1/2, the probability of F is 1/2, the probability of E complement intersect F complement is 1/3. Then what's the probability of E union F complement? Now, number 29, we're asked to find this probability. And for me, I find it so much easier to create a little Venn diagram of what we're trying to find. Okay, so E, of course, is this filled in circle, and then F complement is everything outside of F, which means we're trying to find, this region here. And they're provided certain probabilities, and and I broke this up, I shaded it on this way on purpose. This is the probability of E, which is this. Now everything out here is E complement, which is everything out here, intersect F complement, which is everything out here, which boils down to this outside region, which is that. Well, these two probability are given in the problem, and then when you add those, you get 5/6. Problem number 30. Let x1 through x6 and y1 through y8 be independent random samples from the normal distribution with mean 0 and variance 1. Let z equal to this quantity given. What is the 99th percentile of the distribution of z? Number 30, we're trying to find the 99th percentile of the distribution of z. So that means we need to find p such that being less than p, or the probability of being less than p, is 0.99. Well, z is given to be this. And now this is maybe going to be a common mistake. That well, first we need to transform this into an F distribution, which means it's the ratio of two independent chi-squares. So since the x's are independent of the y's, then this can be transformed into an F. So it has to be a chi-square divided by its degrees of freedom. And I think this is where it may be tricky, is that it's assumed that the mean is 0. Okay? So this sum is sort of complete. So the degrees of freedom associated with this is 6. And the mean of this is assumed to be 0, and the degrees of freedom is associated with this 8. Now, what is a common mistake, I think, for this problem would be if you take xi minus x bar squared, you lose the degrees of freedom for that x bar. But here we know the mean, and it's 0. So you have to be careful there. So this piece is a chi-square with 6 degrees of freedom, and this piece is a chi-square with 8 degrees of freedom. So we need to take the 4/3 over, which is what I do here, and then we need to divide this by 6 and divide that by 8. And then if you do it to one side, you have to do it to the other. So now this becomes an F distribution. Oh, and this is 1. So we get the probability that F is less than or equal to P, where F is a F distribution with numerator degrees of freedom 6, denominator degrees of freedom 8. Look it up at the table and you get P is 6.37. Number 31. Some scientists believe that drug X would benefit about half of all people with a certain blood disorder. To estimate the proportion P of all patients who would benefit from taking drug X, the estimate of P will be P hat, the proportion of patients in the sample who benefit from having taken the drug. Which of the following is closest to the minimum sample size that guarantees that the probability of P hat minus P is less than 0.03, which is all greater than 0.95. Now, number 31 is we want to find the probability, or actually we want to find the sample size that makes this probability, our estimate within 0.03 of the true proportion of people that benefit. We want this probability to be greater than 0.9. Okay. Well, this is an absolute value and a less than, so that becomes this relationship. And now we're going to divide everything by a number, which is this, and this is the standard deviation associated with this difference. It's actually, or the standard deviation associated with P hat, but that's a constant, so it doesn't affect the standard deviation. So then we get this, and this becomes a Z statistic We still want to be greater than 0.95. Now the next step is what can be a little tricky, and I'm gonna wait a second. In the problem, it says that some scientists believe that drug X would benefit about half the people. So they think the true benefit is P. The true people that would benefit is 1/2. So they are saying this P is 1/2. Okay, so because of the problem says 1/2, they think it's 1/2. We're going to plug in 1/2 here. But one note is, if we don't know the true, people that would benefit, one option is pick a value that maximizes this quantity, which then makes this a very conservative interval or an estimate, and it jacks up the sample size needed, but then it guarantees that your sample size is going to be large enough. But the problem said that there was about a half. They think it's about a half. But if that's not given, then you plug in a half anyway, and it really makes the sample size estimate conservative. So then this is square root of this is 1/2. So then you multiply it by 2 up here, same here, which then we get this. And then since this is a z and being between these two, we want to be 0.95. That implies that this endpoint is 1.96. You solve for n, you get 1067 with some change. So to guarantee it, you just take one more and you have 1068. Number 32, consider the following two densities: f0 of f of x equal to 2x, f1 of x equal to 1. Let x be a continuous random variable with density function f of x. The null hypothesis that f of x is equal to f of 0x is to be tested against the alternative f of 1, or f of x equal to f of 1, using a single observation x. The best Neyman-Pearson test with significance level equal to 0.1 rejects the null if. Number 32, we want the Neyman-Pearson test, and so that says to take the simple null over the simple alternative, and if this is less than some k, we're going to reject. So this, but this ratio is 2 over x, and then if you take that 2 over, because that's a constant, this is a constant, you get x. Our rejection reason, x is being less than some constant value. But now we need to figure out that constant value. We want it to be the probability of being less than this when alpha, or when the null is true, we want it to be alpha, the significance level. Well, they provided that. They want it to be 0.1. And let me check. Yeah, 0.1. So the probability of being less than k, which is this, some constant k, although I should use a different k because this k is not that, it is this. Well, you integrate from k to 0 of our, and we're assuming the null is true, which is this, which is 2x. Integrate, you get k squared. Now, if k squared is this, k must be this, and so we reject h naught if x is less than or equal to the square root of 0.1. Number 33, it is hypothesized that an experiment results in outcome k, l, m, and n with probabilities 1/5, 3/10, 1/10, and 2/5, respectively. 40 independent repetitions of the experiment have the results that follow. The chi-square goodness of fit statistic is used to test the above hypothesis. Let R be the observed value of the test statistic, and let S be the critical value corresponding to a significance level of 0.01. What are R and S? Now, number 33 It's a chi-square test. They said R is our statistic, and this is our statistic. And X is how many we observed in category I from our experiments. And then this is how many we expect. So what's the probability? What's the probability, or what are we hypothesizing the probability of being category I is? That's PI. And if we take that times our sample size, that's how many we expect to see in category I under the null hypothesis. And then so you plug in all these values and you get 95 over 124. S is our test statistic. There's 4 categories, so the degrees of freedom is 3. We want an alpha of 0.01. Look it up, you get this, and that's close enough to one of the answers, 11.35. Number 34. Enrolling a pair of fair die, what is the probability that a sum of 7 is rolled before a sum of 8 is rolled? In problem 34, we want to find the probability that we roll a 7 before we roll an 8. So we'll do this in stages. So, and this is the using two die is probably that we roll a 7, or that means that the sum of the 2 die is a 7. Is there's 6 ways to get a 7 out of the 36 possibilities, so it's 1/6. The probability that we roll an 8, there's 5 ways out of the 36. Now the probability that we do not roll a 7 or 8 would be 1 minus the probability that we don't roll this or that. Well, that's this, and then 536 over 636 is 1136. So the probability that we do not roll a 7 or an 8 is 25 over 36. So now this step here, okay, so ignore these 2 lines for now. Let's look at any given roll, the ith roll. So it could be 10, could be 100, could be 1,000,000. What's the probability that we roll a 7 on that given roll and we have not rolled a 7 or an 8 on the previous I-1 rolls? Okay. Well, on the previous I-1 rolls, they're all independent. And the probability that on any one of those that we do not roll a 7 or an 8 is 25 over 36. And there's I-1 of those. So it's this number raised to this power. And then times the probability that we roll a 7 on this given roll is 1/6. And if we call that PI, so that's the probability that we roll a 7 on the ith roll and we do not roll a 7 or 8 on all the previous ones. Okay? But that's for a given, I. So there's an infinite number of possible, rolls. So the probability that we roll a 7 before an 8 is actually the sum of all these probabilities. Well, now let's plug in this value for I, and we get this. And this is a constant. There's no index associated with it. So we can pull it out front, and then let's expand this, and that's what we do here. Well, this is a geometric series, and there's a formula for that, when it's especially with times a constant, which is this. And you simplify that, and you get 6 over 11. Well, that's all I have for today. Hope you enjoyed it. If you did, please like it. And please subscribe so you don't miss the next video. We're going to keep going through these exams until we finish all 8. Thanks. Bye.